Okay, so welcome back. Now, here is the precise definition of a limit. Okay, now this may seem complicated from a mathematical point of view. There's a universal quantifier, an existential quantifier, and then you've got also a conditional in there. So I'm going to go through this. On this video, I'm going to explain as I go along, but in the next video or two, I'm going to break it down into pieces so that we can better understand what's going on, and then it'll make more sense, especially when we get the examples that I'm going to do. You'll see how the formal definition, the precise definition, or what we call the epsilon delta definition of a limit works and how it's applied. Okay, so let's get started. Okay, so here it is. So what this is saying is that it says let f of x be a function that's defined for all x not equal to a over an open interval containing a. Okay, so again, nothing different than we haven't seen before. So we're saying, hey, let the function f of x be defined for all values of a all values of x not equal to a over an open interval that contains a. Okay? Meaning we've got some open interval where a is in the interval. So x, some interval that contains a, right? Some open interval. Okay, so now, then it says let L be a real number. Okay, again, we've seen that before in the informal definitions, right? Now, here's where the precise delta epsilon definition comes in. So again, same conditions, then we would say that the limit as x approaches a of f of x equals L if, so we can say this is true if the following. For every epsilon, so this is symbol for all or every, so for every epsilon that's greater than 0. Okay? What does this mean? What this is saying is that, hey, for any positive distance, so go back to what we were talking about before. So for any positive distance between the function and L, for any positive distance here, there exists a delta that's greater than 0, right? So there's going to exist a positive distance between x and a. Okay? So what this is saying is that if for any epsilon greater than 0, for any epsilon greater than 0, for any positive distance between the function and L, there's also going to be a delta that's greater than 0. In other words, there's going to exist a distance between x and a that's going to be positive. Now, such that, so that's my shorthand for such that. Okay, if this is true, okay, so this is true if for every epsilon greater than 0, there exists a delta greater than 0, such that if this is true, right, then this will be true. Okay? So that means if I choose some epsilon, so this should be true for all epsilon, but let's say I just choose one epsilon. So for any epsilon I choose, any positive value of epsilon that I choose, there exists a delta greater than 0. So if this is true, right, such that if I have this, then I must have this. So if that is true, right, then I have a limit. This is the limit definition. So the limit of the function, so the limit as x approaches a of f of x equals L if, for all epsilon greater than 0, there exists a delta greater than 0, such that if this is true, then this will always be true. Okay, so let's pick this up next time, and I'm going to break this up piece by piece again so I explain it in words. I'm going to go through each of these phrases so that you know piece by piece, and then what we're going to do is do some examples and see it in action, and that will also help solidify your understanding, hopefully. Have a good day.